Hello and welcome to your final exam review notes for Algebra 2. So this means you've made it through the course. Congratulations. Now we're just in our review time so that we can prepare for our final exam. In these notes, you'll notice that a lot of stuff is already filled in for you guys. So stuff that we probably don't need to talk about as much, like exponent rules, having some very basic stuff filled out, adding polynomials. But you'll notice that in these notes, some things are left blank on purpose because that's what's going to guide our video today. So really some conciser notes and just taking us through some different topics that we feel are the most important to make sure we hit because maybe you don't remember it as much. So starting here under the multiplying polynomial section, the thing I deliberately left blank is this binomial square at question 3, where I have 2x minus 3 squared. The big takeaway here that I'd like you guys to have is that whenever you have a binomial square, you should write it out twice and then FOIL or multiply it out. So this would be 4x squared minus 6x minus 6x plus 9, or 4x squared minus 12x plus 9 in standard form. Okay, a lot of times students will think that this is just, oh, distribute the outside exponent of 2 and it's 4x squared plus 9. No. Write it out twice, completely FOIL it out. You don't want to lose out on that missing term. Moving on to the next page. Moving on to long division. So you'll notice that I have the synthetic division filled out. I feel we probably don't have to review that. You can just look at the example and be like, oh yeah, that's how we do synthetic division. Let's review long division though, and I'll actually do it with the same example so that we can see how these methods compare. Long division, if I zoom in here, I'm going to set up the dividend, the thing being divided, under the house of my long division. So just like so. And then the divisor, the thing doing the dividing, goes outside of the house. Now we're going to focus on the first two terms of each. Ask yourself, x times what gives us x cubed? And that would be x squared. Now you're going to take that x squared and distribute it through each term of the divisor. So that gives me x cubed plus 5x squared. And then ultimately you're going to subtract it away. Now, rather than subtracting a binomial, what I can do is add the opposites. So I draw the line, I can change the signs. Adding the opposite is the same thing as doing just our subtraction. Ultimately, I'm distributing that negative. The x cubes will drop out, and we are left with negative 3x squared. And then I just bring down the next term. Now, the process starts over. X times what gives me negative 3x squared, and hopefully you're able to say negative 3x. So again, I'll take that negative 3x, and I'll distribute him to each of these terms. So I get negative 3x squared minus 15x, and I'm subtracting it away. But when I draw the line, I change the signs. So I'm adding the opposites. My 3x squareds are going to drop out. That's on purpose. It's like you're slowly chipping away at this polynomial. And then that leaves me with x. And then bring down the plus 4. Okay, process starts over. X times what gives me x? Very easy. You guys should think 1. Now again, you're going to distribute through. So that gives me x plus 5. I draw the line, I change the signs, so that means I can add my opposites here. And I end up with a remainder of negative 1, which matches what I have up here, the synthetic division. Now, to state my final answer, this is my quotient at the top here, and then I just write plus whatever the remainder is over the divisor, the thing doing the dividing. Now, if I were to truly do this division that you guys are seeing, a cubic polynomial divided by a linear with a leading coefficient of 1, I would probably just jump in and do synthetic division, okay? However, long division is always an option. You would have to use long division if this was, let's say, an x squared plus 5, okay, or a 2x plus 5. So as long as it's a linear function here with a leading coefficient of 1, like x plus 5, x minus 2, x plus 1, things like that, synthetic division is probably the way to go. But you do have long division for those other more complex ones where synthetic isn't an option, but also long division just always works. So that's going through that process. Now, something else students tend to forget in this unit is factor and remainder theorem. And ultimately, this is very simple. If you want to find the remainder of a function, you just have to evaluate at the root of what you're dividing by. So, for example, this is f of x. I want to know what the remainder of this function would be if I divided it by x minus 2. That means you're going to evaluate the function at 2. Notice how 2 is the root of x minus 2. So I go to my graph and I'm like, okay, here's 2. Notice how I come out at y equals 0. So that's the remainder. If I divided f of x by x plus 1, that means the root is negative 1. I go to my graph and it looks like I come out at 4. X has a root of 0. So I go to the graph and it looks like I come out at 0. Now, again, keep in mind that each of these are remainders. So, factor and remainder theorem can allow us to figure out what are factors of our original polynomial. So, fun fact, because we got remainders of 0 here and here, that means x minus 2 is a factor of f of x. And it's the same thing as x. Now, likewise, if you look at the graph here, you'll actually notice we cross the x-axis here at, I believe that's negative 2. So that means x plus 2 is also going to be a factor of this polynomial. All right, something else that we typically have to review is simplifying radicals. So remember, you're just breaking them up into good radical versus bad radical, so perfect square versus not perfect square. And then we simplify. Now, knowing your perfect squares or perfect cubes in the second example is going to be important. Starting with the perfect squares, I know I can break up 75 into 25 and 3. As far as the variables go, I'm going to take every even exponent. But keep in mind that y to the 11th means I have a leftover y to the first that I'm going to put in my bad radical, if you will. Now that I have it split up into good and bad, I just take the square root. Notice how I'm just dividing the exponents by 2, and that's my final answer. Now, as far as cubes go, your perfect cubes are 1 cubed, 2 cubed, 3 cubed, 4 cubed, and so on and so forth. So they're anything of the form y equals x cubed. And they could be positive or they could be negative. If I'm taking the cube root of 54, a factor that is a perfect cube of 54 is 27. So I can break this up into 27 and 2. And then I'm going to take just the divisible by 3 exponents. So this is going to be a y to the 12th that I'm going to take from that 14. Now, that means I have a leftover 2 that I'm going to put in my quote-unquote bad radical. Take the cube root. So now I'm dividing my exponents by 3. Don't forget your cube root symbol. And that's your final answer. Next is adding or subtracting radicals, which it's important to know that in order to do this, you need to have the same radicands. So I'm going to zoom in here. I'm going to take a moment here and simplify just like what I did in my previous example with squares. I'm going to break this up into good radical, bad radical. Take the square root. Which simplifies to 5x squared square root of y plus 2x squared square root of y. Now I have the same radicands, so I can just add, And that leaves me with 7x squared radical y. The last little section here that we have to go through is rationalizing denominators of fractions. And the way that we do this is getting rid of any radicals that we have in the bottom. Otherwise, they're not considered simplified. So in order to do this, with something like a single radical in the bottom, you're just going to multiply by whatever the radical is. And the objective is to create a perfect square. By multiplying top and bottom here by radical 2, you create a 3 radical 4 in the bottom, which is the same thing as 3 times 2, which is 6. In the numerator, we just have 3 radical 2. Just gotta write my 2 there. Okay, now the 3 and the 6 reduce, and we end up with radical 2 over 2. Now, if it's a binomial denominator, then we multiply by the conjugate. So the conjugate looks just like the original, but I just changed the sign in between. By doing this, when I FOIL this out, I have 4 minus 2 radical 2 plus 2 radical 2 minus 2, and you'll notice that the outer and inners drop out. That will always be true when you FOIL out conjugates. So this leaves me with 4 minus 2, which is 2. So now the radical is gone. In the numerator with distribution, I have 12 plus 6 radical 2, and then I'm able to reduce each of these numbers. So 12 divided by 2 is 6, 6 divided by 2 is 3, and that's my final answer. All right, one last little question here, a little extra problem tying into something we talked about earlier. Find the value of m so that it has a remainder of 270. This is going to tie in with our factor and remainder theorem from the previous examples. If I know that this polynomial divided by x plus 5 has a remainder of 270, and maybe I'll just call this polynomial f of x for easiness here, that means that f of negative 5, which is the root of this divisor, must be 270, which is the remainder. So what that means is I can go to this function and I can plug in negative 5 for x. So I'm going to go ahead and do that. And I know that by evaluating the function at negative 5, it should, I just lost my notes here for a second. There we go. It should give me 270. So let's go ahead and clean this up. So I have 25m minus 10 plus 3m equals 270. 28m equals 280. So m must be 10. And that's how you use factor and remainder theorem in order to solve that type of question. So if you wanted to, you really could check this. You could do 10x squared plus 2x plus 30, just putting m back in here, dividing it by x plus 5, and you should get a remainder of 270. But again, just to answer the question, find the value of m using factor and remainder theorem, m must be 10.